It's time for our second keynote speech of the day with two distinguished speakers. They will share their knowledge and experience on federated learning for telecommunications. It's our privilege to introduce our next speakers. Start with Dr. Zhang.
Dr. Zhang is a Senior Partner Solutions Architect at AWS. Prior to AWS, she worked at Fujitsu as a research scientist. She was also an assistant professor at Arizona State University from 2005 to 2008. Dr. Zhang received her PhD degree in computer science from the University of Texas at Dallas in 2005. She holds more than 30 patents and has co-authored more than 100 journal and conference papers in the area of telecommunications.
Also, we have Subhash Talluri, who is the lead AI ML solutions architect of the Telecom Industry Business Unit at Amazon Web Services. He has been leading the development of innovative machine learning solutions for telecom customers and partners worldwide. He brings interdisciplinary expertise in engineering and computer science to help build scalable, secure, and compliant AI/ML solutions via cloud-optimized architectures on AWS. So, welcome to AI Forum 2022, Dr. Qiong and Subhash. Stage is yours.
Thank you very much for the introduction. Now we're going to talk about federated learning for telecommunications. Their growing importance and attention to privacy as represented by these worldwide GDPR fines. There is 20 times fines in 2021 Q3 compared to the sum of Q1 and Q2. Corporations violating privacy regulations, which we anticipated tightening around the responsible use of machine learning, are expected to face higher financial penalties. If we compare the transformative power of privacy enhancement methods, we can see that there are alternatives, like multi-party computation, zero-knowledge proof, and others. Federated learning by far stands out among these options as the most effective. Today, we're going to talk about what is federated learning, why is federated learning growing in importance, and how to build federated learning operations on AWS. And then we're going to talk about federated learning use cases in the telecommunications industry. Federated learning is a distributed machine learning approach that trains machine learning models on distributed datasets. Let's walk through an example. So imagine that there are 5 banks in 5 different countries, each wanting to fight crime. They'd all like to find a better financial crime model. Each of them has their own dataset. Each of them has its own IT group and machine learning systems. And each of them has already detected fraud patterns to fight financial crimes using that data. However, more international banks discovered that their crime has different patterns, and some banks might uncover fraud patterns that other banks have not. So if all these banks would put their knowledge together, they may discover one global fraud detection model and would fight financial crime much better than any of these individual ones. The problem is that none of these banks like to share their data. They each have sensitive customers and have a natural aversion to share customer data with their competitors. Federated learning provides a mechanism to collaborate. It enables sharing data to train a central global model using the customer experience data from all of these enterprises without sharing proprietary data. The terminology here is simple. On the left side, you see the federated learning clients. They can be on premises, at edge devices, or on the cloud. On the right side, we have a federated learning server, which is responsible for the aggregation of a global model. The goal is to improve the accuracy of individual clients' machine learning models while preserving privacy. And we will see other benefits as well later. Individual federated learning clients share their local models to a federated learning server that takes those local inputs and aggregates them into global model. The global model is in turn sent back to each of the federated learning clients. As a result, the global model usually performs better than their local models. There are different flavors of federated learning. And based on features in distributed datasets, we can have horizontal and vertical federated learning. In horizontal federated learning, each distributed dataset has the same set of features. In the example on the left side, you can see that both Bank 1 and Bank 2 have the same features, customer ID, age, and zip code. While in vertical federated learning, each distributed dataset has different set of features, but with overlaps than the ability to map to the same record. For the example on the right side, you can see that Bank 1 and Bank 3 have different features, but they have the same feature, customer ID, to map to the same customer. And based on how federated learning clients are interacted, there are hub and spoke and peer-to-peer mesh-connected clients. And based on when to aggregate at the server, we have synchronous and asynchronous federated learning. In synchronous federated learning, the server aggregates a set of local models after waiting a while to collect this set of models, and then aggregate them into a global model. While in asynchronous federated learning, the server immediately updates the global model once a single local model is received. So why is federated learning important? We have observed 4 benefit patterns for federated learning. The first pattern is cross-device, where thousands or even millions of devices, such as mobile devices, collaborate together to train a global model. The benefit is for privacy preservation. And the use case areas for cross-device federated learning include edge ML, retail, and automotive areas. The second pattern is cross-silo, where tens or hundreds of organizations and the companies work together to train a better model. These organizations and the companies have their own dataset, their own local models, but they can use federated learning to train a global model that is more accurate than their own local models. The use case areas for cross-silo include inter-institutional collaborations, financial service industry, government projects with highly sensitive data. And the third pattern is intra-region training. Due to data localizations, due to operational challenges or high cost of transferring large amount of data to a central repository, federated learning can be used to train models across distributed datasets within the same organization. Hence, the purpose of federated learning here is for cost saving. Its use cases area include applications requiring global reach. And machine learning with larger data size and relatively smaller models benefits more, since exchanging smaller models in federated learning saves more data transferring cost. And the fourth pattern is hybrid cloud that provides operational flexibility for data. In this scenario, a local dataset can be augmented with other cloud available datasets. It is also used in high sensitivity use cases for efficient bursting. When some companies use the cloud just to burst for excessive capacity and need spike, they don't need to move everything into the cloud. You can leave your own on-prem in your own prime environment and still capture and harvest the learning from that. Federated learning can be applied to different vertical industries, such as financial services, life sciences, industrial AI, public sector, telecommunications, and transportation. There are still many challenges in federated learning. One key challenge is data heterogeneity. For example, one dataset has all the cat images, and other dataset has all the dog images. Data heterogeneity impacts the accuracy of global model, leading to more training iterations and longer training time. Many solutions have been proposed to mitigate the impact of data heterogeneity. The second key challenge is privacy preservation. The local models and the global models exchanged between the server and clients may leak private information via reverse engineering. And many privacy preservation approaches have also been proposed for federated learning, such as secure aggregation, local and global model differential privacy approaches. And the third key challenge is federated analytics. Federated analytics provides statistical measurements of distributed datasets without violating privacy requirements. Federated analytics are very important, not only for data analysis across distributed datasets before the training, but also for model monitoring at inference. Despite these key challenges of federated learning algorithm, it is also critical to build a secure architecture that provides end-to-end federated learning operations. The architecture must coordinate federated learning servers and clients for model building, training, and deployment. The challenge for building such architecture include memory and computational constraints, cost optimization, and the billing among the server and clients. So how to build federated learning operations? Here we show the steps for federated learning operations. On the right side, we have the federated learning server, which includes a model registry and some computer resources. And on the left side, we have a single federated learning client, but actually we can have many clients here. Federated learning operations need to provide continuous integration and continuous delivery. Therefore, we need a code repository and for the server and the clients to agree on customized algorithm, such as here, the global, the aggregation algorithm, and also for them to agree on the global model, such as we can use a model.py, and also agree on the configuration information for the server and the clients to interact with each other. So step 0 is to set up the federated learning server and the clients after downloading the federated learning package and to trigger a federated learning training task. Any change in the code repository once agreed upon clients may trigger a new federated learning task. Then step 1, after the task is triggered, the server notifies clients that, hey, the global model is ready. And then step 2, federated learning clients download the global model from the federated learning model registry. And step 3, the federated learning clients start local training, and the local training generates local models. And then step 4, federated learning clients upload their local models and the local model information to the model registry. It may include the number of samples in the local dataset, the client ID, the local training and testing accuracy, etc. And step 5, once there are enough local models collected at the model registry, the server aggregates the local models into a new model, new global model, and then writes it back to the model registry. And steps 1 to 5 is a single federated learning training round. And there can be hundreds of federated learning training rounds until the number of federated learning training rounds reaches a threshold. And then step 6 is to deploy and monitor the final global model at the inference sites. And we can see that the federated learning server plays a very important role here. So who can or should be the federated learning server host? It can be one of the clients, it can be all of the clients, it can be none of the clients. And in this case, it can be the private third party, can be the government, can be the clearinghouse and credit bureau. However, billing, trust and access control among the server and clients need to be carefully considered, and the contractual agreements may be needed. Here we compare the federated learning operations with the machine learning operations. Machine learning operations consist of centralized data preparation, training and tuning, and then model deployment and monitoring. While federated learning operation consists of parallel data preparation at clients, and then federated learning, and the model deployment and monitoring. Actually, the model deployment and monitoring can reuse what MLOps has. Now let's see a demo. Here you see 3 windows. The window on the left side is the server. You may see that it has the AWS step functions. And for the window on the top right is for client 1. And client 1 is at the same cloud account as the federated learning server. It simulates the scenario where you have distributed datasets within a single organization. And for the client 2, which is on the bottom right, it is client 2. It is at a different cloud account from the federal learning server. It simulates a similar, a typical federal learning scenario where different clients can be at a different cloud account. So in the step function, which is the server, we can see that there are step 0, initialize, step 1, notify, and then step 5, aggregate. Here is the client 1. We can see the directory architecture of client 1 and client 2 are very similar. There's a code repo, which is the code downloaded from the code repository, and local data set, and the models, which are the local models generated, and also federal learning client classes. And also there is a local data processing at each client. In the code repo, you may see that we have a cross-account information, configuration information, and also model.py. In this cross-account information, because client 2 is at a different cloud account from the federal server, so you can see that there are several cross-account roles for client 2 to assume in order to access the services at the server. While client 1, there is no such cross-account role to assume. Now let us start client 1. It is under local data processing, and start client 2. It's also under local data processing. Now let us start the server. It is at the step 0, which is to initialize the services needed at the server. And then the server notifies the clients that the global model is ready. It sends out the notifications to the clients. And here, client 1 received the notification. It is at the federal learning round 0. You can see there is a task token, and this task token is corresponding to a specific notification sent from the step function. And step 2 is download the global model. Step 3 is local training, and step 4 is upload the local model and its information to the server. And then go to the step federal learning training round 1. Now we are at the training round 2. And you may notice that we also printed out the training accuracy and the testing accuracy at each client. And actually, after each federal learning training round, you may notice that those training accuracy and testing accuracy are gradually improving. And at the server side, you can see that there is a condition satisfied, which is to check if the current constraint, here we configure is the number of federal learning training round reaches 8. If this constraint is not satisfied, it will go for next training round. If it's satisfied, it will go to the step of yes, end the training. Now we are at the federal learning training round 4 and 5. Since our federal learning training round starts from 0, so it will end at the federal learning training round 7. Now we are at the 6 and training round 7. That is the last training round. Now the training ended, and you can see that the step 6 comes is to download the federal learning trained global model for deployment. Okay, so how to build such platform? So here we show the reference architecture for such platform. We have a federal learning server on AWS and the federal learning clients on premises and on also another federal learning client on AWS cloud. On the server side, we have AWS step functions, iterate federal learning training rounds. And for each training round, the step functions sends out SNS notification that are queued by Amazon SQS. And each federal learning client has a corresponding SQS. And the federal learning model registry consists of Amazon S3, storing the global and the local models, and also DynamoDB storing the local model information. And here we also enable DynamoDB stream to trigger AWS Lambda. Whenever a new local model is collected, AWS Lambda is triggered to check if there are enough local models collected. If yes, the Lambda aggregates the local models into global model. And the resulting global model is written back to the Amazon S3. And the AWS step functions then determine if the federal learning should be terminated based on some constraints. And here we say that the number of training rounds reaches threshold. And on the client side, the on-prem federal learning client uses AWS SDK and CLI to securely access the services at the server. And the client on AWS can use a private link to access the services for secure communication. There are several advantages for this architecture design. First, it uses cloud-native services that have proven security and operational excellence. It's built from ground up for federal learning, so that you're able to run customized federal learning algorithms in those cloud services. Second, there is no direct write from the server to the clients. Instead, the clients are able to pull and push information to the server based on their own willingness. The clients will be safe and no internal system to be shared by outside entities. And third, here we have the server uses serverless services instead of using a persistently running server, which reduces the computation cost at the server side. Now I will hand over to Subhash to talk about federal learning use cases in telecommunications industry.
Okay, hello everyone. Thank you, Dr. Zhang. Thank you for that first half of the session. So now that we have looked at what federated learning is, and we've also seen a demo on how it was developed on AWS, we want to now look at some of the use cases, and particularly, the application of federated learning in the telecom industry. So the objective here is to really motivate all of you to look at federated learning as a way of problem solving for some of the challenges we have, and we'll talk about 3 different use cases in the next few minutes. So the first one is the application of federated learning for telecom fraud detection. So the use case here is, as you can see on the top left, is a roaming scenario. So how do we detect roaming fraud scenario that communication service providers often face? Here you see that a subscriber who is part of a home network is now roaming in a visited network, and there's a data exchange between the visited network and the home network that happens through file exchange in the form of near real-time roaming data exchange. So the roamer might be placing originating call and terminating calls from their device, and this can take many different type of fraud scenarios, such as international revenue share fraud, roaming abuse fraud, permanent roamer situation, etc. Now, if on the right here, we have seen the concept of federated learning, and we try to now put them in the context of communication service providers. There are, let's say, in this example, there are 3 of them, CSP A, B, and C, and each of them run their own local training for fraud detection. Now, the problem with that is because fraud is a rare event, it is an anomalous event, the number of data points tend to be very less. which means the imbalance in the data is quite high. So typically when, let's say, one CSP runs their machine learning training, they would aggregate home network data and their roaming ADRs, roaming data that comes from the visited network, combine them, aggregate, enrich them, join them with their ground truth data and do iterative machine learning to be able to identify fraud. But because of lack of enough data points, it might be the large imbalance problem leads to poor model performance. So what we propose here is basically if with the federated server, if multiple CSPs, communication service providers, can take all their learnings, assemble all those local models, and send those local updates to a federated server, and the model weights that are shared by the global model can do a much better job at detecting telecom fraud. So this is one use case in telecom. The next one I want to talk about is personalized customer experience for ride hailing. So you might ask me how this is related to telecom. Let's say you have a ride sharing service. Yeah, there are a number of cars. The idea here is, when a rider is in an active ride, they're probably not doing anything. So here, the CSP might want to have a tablet for which the connectivity is provided by the carrier, and it's a device that's owned by them. And the objective is that that particular tablet being able to detect whenever there is an occupancy, and the data concerning an active ride comes from the ride sharing service. And once a human is detected, they would open up their, they'll have that tablet available to that rider to have some personalized experience and interaction with it. Now, in this case, there are two challenges. One is the human detection needs to happen through the tablet's camera, which means it needs to take an image without permission. So that leads to privacy issues. Now, this is where federated learning can come in place, where the moment a picture is taken at different timestamps, in order to detect whether a human is present or not in the back of a car, they could, it would do a local training based on, basically a local model that's deployed on each of these tablets. And all of them, they share those weights to a federated learning server. And immediately after the local training happens, the image is purged. So the image does not leave the device and nobody has access to it. And the lifespan of that image is quite short. So in this way, the privacy concerns are addressed, and at the same time, you're able to give personalized experiences to the riders in a ride-sharing service. So that's the second example. The third one I want to talk about is equipment monitoring for rare events. Now, the flavor that this can take in terms of telecom is all CSPs, they have huge data centers and different equipment that are mission critical. So that means, and they're backed up with power, right? And there could be generators that are supplying this power to all these mission critical systems. In this scenario, what happens is the use case here is you have a thermal camera in a generator room that's supporting a data center of a communications provider. And the idea is to detect leaks using heat signatures from these thermal cameras. Again, it's based on image recognition, These images would be assembled. The local training happens at each of the individual sites. All those local training is transferred over to the federated learning server, where a global model can learn better with all the information that's coming from multiple sites, and then have a better performing model that can be deployed at each of these individual sites. So these are the three use cases when it comes to federated learning. And when it comes to closure, like despite the challenges in FL, we are seeing tremendous potential. So this is in the case of personalized federated learning, the increasing regulatory pressure on ML, even in large language models, which is a fast evolving space, FL experiments are showing promising signals. So our call to action to all of you today is, try to look at solutions that can leverage federated learning and federated learning operations. We are happy to co-build with you for the challenges and for different architectures and the use cases. We'd be very happy to work jointly on your use cases. Please do email us if you'd like to work with us.
So let's start the Q&A session. The first question is for Dr. Zhou. Will federated learning help to achieve strong AI?
Federated learning majorly is for training machine learning models. One typical machine learning model trained by federated learning is neural network. It can be ANN, can be CNN, can be RNN. So if strong AI is enabled by deep learning neural networks, yes, federated learning is able to help.
The next question is down to you, Subhash. What are the applications of federated learning in the metaverse?
Yes, thank you for that question. While when it comes to metaverse applications, I would probably answer this with respect to the back end, where the spatial computing that is necessary to support applications for metaverse. In such a scenario, federated learning, especially learning on the edge devices, can certainly help.
Okay, Dr. Zhou, any ML algorithm can be trained as FL model, or do we need specific algorithm for FL?
The typical model of machine learning algorithm is neural network. Yes, you do for some different models, you may need different algorithms. And another popular actually is under research is having XGBoost model to train on federated learning. And some other models are not, right now is not commonly trained in federated learning and is under research.
So Subhash, will model overfitting happen to the local training environment in this process?
Yes, that can certainly happen. Now, the example that we have just talked about that uses telecom fraud detection uses autoencoders, which is for anomaly detection. Whereas, the other examples were around image recognition. Now, that said, model fitting can certainly happen. The local training is up to the organization that's conducting it, and the same standards and protocols that you would follow when it comes to looking at model performance, all that will apply with the enhancement of federated learning server that can make these models much better at a global level.
Last question is for last question is for Subhash again. So AWS already has standard telco data around the globe since it hosts many telco data lakes. Do you have already built FL global mods built using those data that we can use today?
No, not necessarily, because every customer who uses AWS uh, get their own part of the cloud where they're operating in. So that means all the standards and compliance and security are in place. So they own the data. The security of the cloud is the security of the cloud is the responsibility of AWS, but security in the cloud is responsibility of the customer. So that said, all data is with compliance to all the standards. So the access is only available to the customers. So that means we cannot enable such type of cross-learning unless there's mutual agreement in place.